Polar coordinates part one. In polar coordinates, if we change the angle theta and change r, we end up with a small element of area like this. It's not a rectangle, it's like a piece of a sector of a sphere. And it turns out dA is equal to r times dr times d theta. That's what this little piece of area equals, and that's what we have to integrate. Here's a very simple algebraic demonstration. Suppose we have two concentric circles, radius Ri and Ro. The difference would be dr, of course. That would be just the difference between Ro and Ri. Suppose this is the area here. dA is this piece right here. And suppose all the way around the area of this ring is we'll just call area. And this is d theta, small change in angle. Well, the area is going to be the outer area minus the inner area, pi r outer squared minus pi r inner squared. And we can set up a proportion. dA is the total area as d theta is to 2 pi, the angle of one revolution. Now it turns out you can solve for dA, bring area up here, replace area with this, d theta over 2 pi. I skipped a lot of algebra steps here. You can cancel out the pi's, actually, get rid of that. And then Ro squared minus Ri squared factors is that times that, difference in two squares. Move the 2 under here. And then that's just an average R. That's dr, and that's d theta. And that's where the r dr d theta comes in an integration process. This dr shrinks to 0, so there's no average, it just becomes r. So consider the following integrations. Number 1, suppose theta goes from 0 to 2 and r goes 0 to pi and r goes from 0 to 2. The area or the region of integration, theta goes from 0 to pi, r goes from 0 to 2. That's just a half circle. And conceptually speaking, what happens is we break this up into these little pieces. Theta goes from 0 to pi, and for each theta, r goes from 0 to 2. So we would have these little concentric circles. We add up all those little pieces, it gives us the area. Now, you can calculate this as 1/2 pi times the radius squared. Number 2, let's suppose we do 0 to pi over 2 and 2 to 3, r dr d theta. Now theta going from 0 to pi over 2, that limits us to quadrant 1, and the radius starts at 2 and goes to 3. So we're going to have a region of integration like that. And we can compute that. You could do 1/4 pi times 3 squared minus 1/4 pi times 2 squared. The whole circle would be pi 3 squared minus pi 2 squared, but you have to take 1/4 of it. So here are a couple more examples. Suppose we have integral from pi to 2 pi and integral from 1 to 2 r dr d theta. This would give us, now we're going from pi to 2 pi, So that would be down here. This region, that would be 1, that would be 2. Now we can compute that area as 1/2 pi times 2 squared minus 1/2 pi times 1 squared. That's 2 pi, 4 divided by 2 is 2 pi minus 1/2 pi, which is 3/2 pi. Now, just for completeness sake, how about if we evaluate one of these integrals so you can see it done? We work from the inside, just like a dy dx integral. R dr integrates to r squared over 2 from 1 to 2 d theta. Okay, and that's going to give us, let's come down here so you can see the light might have blotted that out. R squared over 2 from 1 to 2 d theta. So we can plug in 2, plug in 1, we get integral from pi to 2 pi, 2 minus 1/2 d theta. And that's equal to 3/2 theta from pi to 2 pi, which is 3/2 theta, 2 pi minus pi. And that's just 1 pi, so we get, yep, sorry about that, there's no theta there, my mistake. 3/2 2 pi minus pi, which is 3/2 pi. And that's exactly as we computed before. So, okay, that's part 1. We'll be back for part 2 shortly.